Hello everyone and welcome to another video. Today I'd like to continue our exploration of partial differential equations by revisiting the wave equation, and this time looking at how it behaves if there are two spatial variables. You might recall that some of our previous videos investigated deriving the one-dimensional wave equation. We saw how this was a great way to model a system such as a vibrating string. If you haven't already viewed it, I would recommend stopping and watching that video first before continuing on with the discussion. I will leave a link to that video in the description below. So, for now, why don't we turn our attention to two-dimensional membranes, such as something like a drum head. For those of you who have watched some of my other videos, I think you know that I'm not the best artist in the world, so instead of trying to draw a diagram of what we're talking about today, I thought it might be easier if I try to make a physical model of the system we're trying to work on. So, in this case, I'd like to take a membrane of some sort. In this case, I've, quote unquote, borrowed one of my wife's towels here. And you can see here is what I want to do here is introduce some tension to this and impose a boundary condition around some region on this membrane. So to do that, I'll also go ahead and use this spring-form pan that I also quote-unquote borrowed from the kitchen here, and I'll just wrap this guy around it here, and let's see if I can maybe secure the edges here with a rubber band here. And what I'd like to do now is hopefully be able to introduce some tension on this membrane. This is actually a lot harder than it looks to do without an assistant or without a flat table to work on, but I think I can get this to work. Okay, here we go. Okay, all right, so now this seems pretty reasonable. So I'm trying to introduce a uniform tension along the face of this membrane here, and we can see now that we've constrained the edge of this membrane to not move. So now if I impose some kind of initial condition, for example, like flicking the back with my finger, you can see this vibrate, right? And it wiggles. I don't know, can you see that? Maybe if I get a little bit closer, maybe that might be easier. If I flick this, you see we get some vibrations in here. I don't know, that still seems a little bit difficult to visualize. So maybe here, to help us see the vibration here and to convince you that this surface is actually vibrating here, I've also, on my theme of borrowing stuff from people, I've used some of these beads from my daughter's art kit. So let me just sprinkle these around the surface now. And what I'd like to do now is if we also now get this thing to vibrate, you should be able to see these beads kind of, whoa, crud. Whoops. Okay, that vibrated a lot more than I expected here and kind of made a giant mess. Oh well, it doesn't matter. I've got two small kids and a dog in the house, so when somebody finds this mess in the morning, I'm just going to blame it on them. But anyway, I think that sets the stage here of what we'd like to do. So let me see. What we could do here is I would like to derive equations of motion for this system by considering a small area, some dA on this membrane. So, you know what I really want to do is I kind of want to draw on this so we can see like a coordinate system, but I wonder if my wife is going to miss this thing. Hey, hon, I kind of want to draw on your towel. Let me know, is that a problem? Okay, I didn't hear anything, did you? Let's go ahead and do it anyway. So let's proceed. What I would like to do in this case now is let's attach a coordinate system to this membrane here. So maybe I'll draw like, let's make an X direction here in this way. I'll label this here as maybe X here. And then we'll have a Y coordinate in the opposite direction here. And what I'd like to consider now is a small chunk of this membrane, and we'll call this thing dA. So maybe I'll draw a little rectangle. I guess it's pretty big here in this picture just to make it show up here, but let's say that it has a width here of delta x, and it has a height here of delta y. So this is this small little chunk of area that I'd like to consider here. Okay, so what I'd like to do now is think about, can we find a function here that describes how any bit of this membrane deflects in and out of the plane at any spatial coordinate x and y and at any temporal coordinate time t. So that's the plan of attack. Why don't we go ahead and draw a diagram here on the whiteboard so we can add some details of what this little area dA looks like. All right, so to get equations of motion, let's first start off by writing a couple of assumptions for this problem here. So the first assumption here is let's go ahead and assume that the density is uniform. So in other words, this is something that's made out of the same material, and it's the same everywhere here. So the density, we're actually going to measure this in units of, say, like kilograms per meter squared. So it's a mass per unit area here, and we want to consider this being constant over the entire membrane. Okay, so that seems pretty reasonable here. 2 here, let's assume that the membrane is perfectly flexible. So membrane is perfectly flexible. So in other words, it has no resistance to bending. Okay, so it's a thin membrane in that case. This is not good for like a piece of sheet metal, which definitely has some resistance to bending. This is more like for pieces of thin rubber or latex or cloth or things like that, right? Okay, so assumption 3 here, membrane is fixed along the boundary. So this is not going to really play so much into the derivation of the partial differential equation for the system right now, but it will definitely come into play when we actually try to solve this and apply some boundary conditions. So let's consider a fixed boundary condition here. 4 here, let's assume that also the tension is uniform and constant. So the tension, again, let's use units here of force per unit length. We're going to see in a second why we're using this measurement of tension here. Again, this is not like a single string where, yeah, there's definitely a clear single value of tension throughout the string, right? This is now a membrane where the tension is spread out over the entire surface. So to make the units and the math a little bit easier, let's just conceptualize tension as force per unit length here. And we're going to say that it's the same everywhere and it doesn't change. Even if the membrane is vibrating up and down here, it's going to basically be the same tension everywhere. Okay, and finally, assumption number 5 here is that out of plane deflections are small. Right? So really what we're looking for here in this case is actually this function u here, which describes the out of plane deflections of this membrane at any given x, any given y, and at any time t here. And we're going to assume that these are small relative to the geometry of the rest of the problem. Okay, so with these assumptions in mind, I think we can go ahead and draw a diagram of this system here. So maybe let's do it like, I want to try to make sure I use the board space intelligently here. Let's draw it over here. So what I'd like to do first here is let's just draw a diagram of this system kind of in the x, y direction here. So we've got some kind of large membrane. So like, in this case, it was our big dish towel here. But what I would like to consider now is a small area of this dish towel that we'll call some rectangular chunk dA. Okay? And we said that, all right, the left side of this chunk here is at coordinate x. And the right side of this chunk here is at coordinate x plus delta x, right? If we consider this thing having a width of delta x here and a height of delta y, right? This is where the left and right side of this thing are located. We can do the similar for the bottom is located at y, and the top of this thing is located at y plus delta y, right? All that seems pretty reasonable. Okay, now, what might be helpful is let's draw a larger version of this picture here, and we'll do this in 3 dimensions here. So let me just draw a 3-dimensional coordinate system first here. So here's x, y, and then z, which is actually our deflection, right? Out of the plane here. So what I'd like to do is I want to get cut this little chunk of surface out here from this top view and place it in this 3-dimensional view. You know what actually might be helpful? Let's actually physically cut out this dA out of our membrane, right? This thing's already a goner here because I think I already drawn it with a Sharpie. So I think I'm gonna get in trouble anyway. So if you're gonna get in trouble, let's just go the whole 9 yard, the whole distance here. So I'm just going to cut out my little chunk of the membrane that I'm interested in. And again, this is difficult to do here. Boy, I wish I had a table or something, but I guess it might make it a little hard. Okay, so let me cut this thing out. Almost there. Ah, whoops. All right, it's falling apart. All right, tell you what. Switching tools. Let's just use scissors here. I do need an assistant. I should get my little daughter to do this. She is like really good at cutting things out. She's in kindergarten right now, and I think in kindergarten, all you do here is work on gluing and cutting things. So she's an expert at this kind of stuff. All right, here we go. I've cut out my little chunk DA here, right? So again, what I want to do is take this little section here, overlay it in space here, and then let's draw a rough picture of what this thing looks like, right? So let me grab a pen here. Maybe the easiest thing to do first is to draw its projection into the XY plane here. So maybe I'm going to draw it like this here. All right. So here's its projection in the XY plane here, right? The left side of it, again, we said was, whoops, actually, that should not go like that. That should go like this, right? So here's X. Here's X plus delta X. Here is Y. Here is Y plus delta Y here, right? And now these points can get projected up to where the surface is actually located, right? So maybe we will draw it like something like okay, something like that, I think is a halfway reasonable drawing of this membrane here, right? Okay, so now what I'd like to consider here is let's consider what kind of forces are acting on this membrane here. So along this front face here, right, that we've cut out, there's going to be some force that if we look at sort of the average value here of where this is angled here, you're going to have some force like this coming off of this face, and the magnitude of that force here, right, isn't this going to be something like the T times the distance, right? So that'll give us the units of newtons or units of force. So it's basically the tension times the distance or the length of this edge here, right? And we see that the length of that edge is just delta x. So this force here is T times delta x. Similarly, on the back side, you're going to have another similar T times delta x, but it's going to be oriented and pointed in a slightly different direction because, right, we're taking this funny membrane here, and this thing is laid out and it's draped over in a surface. So the front face and the back face and the left side and the right side, they're all pointing in sort of different directions. And furthermore, the slope of that pointing changes as x and y change all over the face here, right? So we'll investigate that again in a second, but okay. So we get up these on the front and the back face. Similarly, on the left and the right side, we also have forces acting on this of T times delta Y in this case, and also T times delta Y. All right. Okay. So it actually might behoove us now to look at a planar view here. Let's just look at this in the XZ plane. So let's draw that a little more cleanly down here. So if I draw this like such, here you got X and Z, which is really our deflection, U of X, Y, all right? So in this case, again, let's use the same color here. You got your membrane here, like such here, and this is now located here at X here, and again, this is located at X plus delta X, right? And we got the force over here of magnitude T times delta Y, right? And over here you got T times delta Y here, right? And again, this picture is slightly misleading again here, right? I've drawn it like it's sort of making the assumption that, you know, again, here's our little area, delta X, delta Y. We're now looking at it directly kind of on an edge here. And the way that picture is drawn, it's basically, it's misleading in the sense that I don't think I can get the camera angle right. It's something, so, geez, yeah, I can't. It's something like this here in that picture where it makes it look like there's no variation in the surface as Y moves, as you go in and out of the board. But one of these edges, you know, maybe that back edge is tipped up quite a bit. So you definitely can see that there is some variation in slope as you move in the Y direction here. But what we're drawing here on this board here is, let's consider this to be sort of the average angle here of this membrane as you move along that direction. So in other words, what I'm going to assume here is, let's call this angle here alpha, and that is this average angle here of where this average aggregate tensional force on that edge acts. Similarly, on the other side, we can do the similar thing here. Let's call this angle here beta for that average angle. Okay, great. So with this, I think we're pretty good to go here. Let's go think about how can we go ahead and derive now some equations of motion based on this system, right? We have effectively a free body diagram of our system. So let's just go ahead and apply Newton to this. So first thing is, let's consider this thing in the horizontal direction, right? So let's look at horizontal forces, right? So just looking at that free body diagram, let's look at this in the x direction here, right? So we basically have some of the forces in the horizontal. I guess if you want to look at it, well, I guess what's a better notation for this? Because this is all sort of horizontal. Well, this is probably fine here. Horizontal, right? So in this picture down at the bottom here, right, we basically have something like what? It's t delta y times cosine of beta, right, minus t delta y cosine of alpha here, right? And due to our small angle approximation, right, we said that, all right, these small angles are basically 1 here, so we end up with 0 here, right? So this is great. What this shows us here is there's no horizontal forces in this situation due to our assumptions, which basically means, right, no horizontal motion. So the only motion this membrane is going to experience is in the vertical or the out of plane direction. So let's look at that right now. How about vertical forces? All right, so in the vertical forces, right, we can also do a similar thing. Some of the forces in the vertical direction, right? Okay, so just looking at that picture, we got what? T delta y sine alpha, or no, sorry, excuse me, sine beta, right? Sine beta. Minus t delta y sine alpha, right? So you got this force going up, you got that force going down. I just look at the vertical components here. And now let's go ahead and use our small angle again. Approximation, right? Which basically said if you had, you know, sine of some small angle, let's call it theta here, right? Didn't we say that's effectively theta here? Or the more useful way to look at this is effectively tangent of theta here, right? Those are all the same thing because tangent is right. It's just sine over cosine. We said earlier cosine was just 1. So this is all approximately reasonable here, right? So let's plug in this expression for tangent into these over here, right? So what we end up with here is some of the forces in the vertical, right? We could just write this thing as t delta y times the quantity tangent beta minus tangent alpha. Right? Okay, let's look at what are tangent alpha or tangent beta and tangent alpha. Let's look at tangent beta here, right? Tangent beta is, if you come back over to this picture, tangent is opposite over adjacent here, right? So it's almost like rise over run here, which is effectively the physical slope of this system here at the right edge in this case. Correct? So what we see here is basically tangent beta is the same thing as partial u with respect to x at this location. So maybe we should write that down here. Let's write this real quick here. So we can say that tangent beta here, right, is basically partial u with respect to x evaluated at x is equal to x plus delta x here, right? And at some y value of, again, we got to be a little bit careful here. Well, actually, no, we don't have to be careful, but I like to be kind of cautious about this here. So this is at some, again, the y location, this can change here, right? So what we want to note here is let's just pick some y1 value, which is in between y and y plus delta y here, right? Because again, all we're trying to do here is basically say that over here, this was tangent of this sort of average aggregate angle beta here, right? Well, I want to equate that to the physical slope here. But again, we talked about earlier, the physical slope of this thing in the x direction is changing as y goes in and out of the board, right? So I'm just going to pick some value y such that the right-hand side equals the left-hand side. Again, it's if you want to just boil this down or reduce, it's just like we're looking at averages here, okay? Okay, so that's great. We can do the exact same analysis for alpha here, right? This is du dx. So again, tangent alpha, if I look at this picture, it is opposite over adjacent on this side, or rise over run on this side, or physical slope of u with respect to x here at the left side of the piece of a membrane here, right? So this is du dx evaluated at x equals, and at y equals some other y2 value, how about, between y and y plus delta y, right? Okay, what's alternate notation for both of these? We could also say that this here, you know, you could also write this as ux here at x plus delta x and at y1, right? And similarly, this thing is, the shorthand notation would be ux at x and y2, right? Awesome. So let's substitute those in for this expression over here. And what do we get here? So we get, oh, and actually, sorry, vertical force. Maybe we should have said this is sum of the vertical on the left and right side, right? Because we actually haven't dealt with the front and back. We're going to deal with that in just a second here. So really, so we get tension delta y times ux of, where was it? Yeah, here, x plus delta x and y1, right? Right? Minus ux at x and y2. Right? Okay, great. This was some of the forces in the vertical on the left and right side. Okay? You can do the exact same analysis for the front and the back face of this object here, right, of this small dA, and you would get virtually the identical expression here. So let's just write that down, what you would end up with. You'd end up with sum of the forces in the vertical on the front and back faces here. It's going to be tension delta x here, and now you would end up with uy at, again, some average value like x1 and y plus delta y here, minus uy 2 at y. Great. Okay, so the total sum of all of the forces acting on that little object here is just this one plus this one here. So I think we're in a good spot to apply Newton here to look at the total motion of this system here, right? So Newton's second law is going to govern this here. So let's go ahead and write that down. So Newton's second law, right? Which was just mass is, let's do this. Mass times acceleration is equal to the sum of all of the forces, right? And if we're looking at this in the vertical direction, maybe we can add little subscript v's here, okay? So, all right, what's an expression for mass? So the mass of this thing is the density here, right? Remember we said that this was units of kilograms per meter squared here, right? Or mass per unit area. So I got to go ahead and take this density here, multiply it by the area of that thing dA. Well, the area of this thing is just delta x times delta y. Right? Great. So here's our mass times acceleration in the vertical direction. I think everyone would agree that that's just, here's the deflection in the vertical direction, or the position. So if I take its second derivative with respect to time, I get acceleration. So here we go. Mass times acceleration is equal to this garbage down here. So let's write that down here. So it's t times, well, gosh, I don't really want to rewrite it. Tell you what, let's do this. It is this garbage, junk, how about junk 1 plus junk 2? Okay, just don't want to write this all again here because I want to make a simplification here. So now let's go ahead and isolate the u double dot here. So I'll divide through by all of these gobbledygook numbers here, right? So we end up with the left-hand side is just du squared dt squared is equal to, this whole other side can basically reduce to tension over density times ux of x plus delta x y1 minus ux x y2 all over delta x here, right? This plus, you get a very similar term, uy x1 y plus delta y minus uy x2y all over delta y here. And let's close this square bracket to match that. Okay, all right. I want to look at this term right now. In fact, let's look at the numerator here. So the numerator here is, what's this first term in the numerator? This is the slope at x plus delta x. So this is effectively slope at the right side of the membrane minus this here is slope at the left side of the membrane. So the entire numerator is basically the difference in slope, or how much did the slope, the slope in the x with respect to x change, so here's like a rise here, right? Or how much did the slope change? And here's your run as you move over a distance delta x here, right? So if you think about this long enough, this is rise over run. It's basically asking how did the slope change as you move from delta x here? Or it's basically saying this is uxx, right? Similarly down here, this term right here, this is slope with respect to y on the back face minus slope with respect to y on the front face. So the numerator of this term is basically how much did the y slope change over a run of delta y. So this here is uyy. So awesome. This whole thing now can be rewritten in a nice compact form here of partial u squared with respect to t squared is equal to t over rho times uxx plus uyy, right? Let's just call this thing, this is some constant, right? It's just tension over rho. This is like a c squared here. And if you look at this long enough, right, doesn't this look just like it should be ringing some bells from our vector differential calculus discussion. This is just Laplacian of u. So the nice compact format of this is basically partial square u with respect to t squared is equal to some constant c squared here times the Laplacian of u. And here you are. Here is our 2D wave equation. Right? And in this case, again, maybe we should fully write this out here. So here, c squared is tension over rho. It's just some number here associated with your problem here. And again, if you look at this long enough, if there was only one spatial dimension, like if there was no y, if this was gone, right? We recover basically our 1D wave equation. So maybe the more efficient route to have this discussion is we should have done this first and then simplified it to the 1D wave equation. That's the other way you could have skinned this cat here. So now that we've got the actual, here's our 2D wave equation, let's go ahead and think about solving this thing now in the next lecture. All right? So I think this is a good spot to stop. So if you like the video, please subscribe to the channel. It really helps me continue making these videos. And I hope to see you at the next video when we will solve this for actually 3 independent variables, right? An x, a y, and a time. So I hope to catch you then. Bye.